So some of Dalton's ideas were mostly right, but not exactly right. One of the things he said was that atoms are indestructible. Can atoms be destroyed? Sure they can. It's called a nuclear reaction. But what he said was true if we stay away from nuclear reactions. Atoms are actually composed of smaller particles. And J.J. Thomson, another British scientist who lived around the turn of the 18th century, the 20th century. I always forget that. I try to avoid saying that, and then I just blew it right there. 20th century. He only died in 1940. That wasn't so terribly long ago. He discovered a smaller particle than the atom called an electron. The electron has a negative charge. It's much smaller, both in size and mass, than the atom itself. And it's uniformly present in many different kinds of substances. So it wasn't just that carbon had electrons, but every substance that he examined had electrons in it. And so then the idea was, well, it's got electrons. They have a negative charge. There must be something in there that has a positive charge because we can tell that all matter is not charged. So his idea is called the plum pudding model of the atom. Anybody ever had plum pudding? Or do you know what plum pudding is? See, this guy was British. I've never had plum pudding either. The closest thing Americans have to it would be like a blueberry muffin. Okay, so you've got a muffin and it's got blueberries in it. The blueberries are pretty random, or a little bit like a chocolate chip cookie, perhaps. You've got these little bits of chocolate or blueberries spread throughout the rest of this stuff. So here in this illustration, the pink stuff here would be like the cake part of the muffin, and these electrons are like the blueberries, and they're scattered around. These are negative, and there must be some positive charge. So that was the plum pudding model. Rutherford, in 1909, did an experiment. He actually was a colleague of Thomson, and he was trying to show that Thomson's model, this plum pudding model, was correct. And so this is an experiment that he did. He took a very thin sheet of gold foil, and he shot alpha particles, which are small positively charged particles. He shot it at this gold foil, and what they expected was that the particles would go straight through, and most of them did. But some of them went off at a little bit of an angle, and some of them bounced back. And this was very, very unexpected. In fact, he said this was as surprising as if you shot a cannonball at a piece of tissue paper and it bounced off the tissue paper and hit you in the face. That would be really surprising, right? They were not expecting these particles to bounce off. They were expecting them to go straight through. That this led to the discovery of the atomic nucleus. This is what they expected would happen. We have these negative particles here, and the alpha particles were supposed to just go straight through. But what actually happened is that some of them bounced almost straight back, and others were bent at an angle. And this led to the discovery of the nucleus. Because the nucleus is a very small, very dense, positively charged section in the middle of the atom. And when these positively charged particles came near the nucleus, the positive charge of the nucleus deflected the positive particle and caused it to bend away. And if it hit closer, it would bounce back. So this led to the nuclear theory of the atom. And the nuclear theory says that most of the atom's mass and all of its positive charge are contained in a small core called the nucleus. So instead of this like big piece of cake being the positive part with some electrons sprinkled around, Now they're saying all of the charge is concentrated in the middle of the atom. It's very tiny. Most of the volume of the atom is empty space. And in that empty space, we have these tiny negatively charged electrons. So just to give you an idea of the relative sizes of these things. If the nucleus was the size of a green pea, so about that big, one of those, frozen green pea like your mom made you eat when you were a kid, and you put that on the 50-yard line of a football field, the edge of the atom would be at the goal lines. So the nucleus the size of a pea on a football field. The atom is much bigger than just the nucleus, right? And the electrons are about 2,000 times smaller than the particles that make up the nucleus. So you've got a few electrons in this volume. Think, we're talking a distance across, the diameter of the nucleus of the atom being the length of a football field, 100 yards. Think that's now a sphere that's 100 yards across. And in that whole volume, there's 10, 20 electrons that are much, much smaller than that green pea. Most of the atom is empty space. There's actually very little inside of the atom. And then you look at the bench, and you can hit this bench. And it seems pretty hard, doesn't it? And yet it's actually mostly empty space. The nucleus, if you could just take a whole bunch of nuclei and squish them together, squish out all the empty space, and just concentrate nuclei into the size of a period in your book, little tiny thing, it would weigh millions of tons. Because almost all the mass of the atom is in the nucleus, and it's so tiny compared to the size of the atom. So, nucleus is very small, positively charged. The number of electrons, the electrons are the ones that are negative, the number of electrons equals the number of positively charged electrons inside the nucleus. So we have, here's the nucleus. Inside the nucleus are two kinds of particles, protons and neutrons, and then outside the nucleus are the electrons. Let me find a color here that we can see on the black. Positive proton. The protons are positive.